Hello, everybody. Today, we are going to have a podcast about essence of science about 3D printing. I'm Dr. Abbasi for Essence. Amanda is not here today with us, but I have a special guest. Please go ahead, Liam.
Hi, I'm Liam Groom, and I am a biomedical engineer with a strong interest and experience with 3D printing.
Well, what is a biomedical engineer? First of all, explain to us. What is that?
So a biomedical engineer can be a lot of things. I focus a lot on mechanical design as well as kind of cellular biology, mechanobiology, biomechanics. Yes, those are two different things, but include everything from quality engineering to production and human factors design. So there's a lot of things that it can include.
Practically, you design and stuff that doctors are going to use for
Yes.
in human body.
Yeah, that is
So,
what I do.
yeah, and and obviously 3D printing, everybody has heard about that.
Mhm.
And some say that probably that's one of the most important invention of 21st century, the 3D printing. What do you think? What are the other, really game changer technology in 21st century
Hmm.
besides 3D printing?
Well, I would be remiss to mention the development of large language models and AI. That's a little
AI,
bit overblown in media at the current state of things.
3D printing technology, AI, and I think it's fair to say the self-driving car, which is related as partially, not completely to AI. I think these are really the changes that are going to come from these three technology are going to really be tremendous, and it's going to be involving everybody's life.
I
Now,
was going to say that protein modeling is going to be probably the biggest single technological advancement of the last 10, maybe even 50 years, because now that we have computers that are able to create custom proteins, we're going to be able to create drugs and medications that are able to treat any disease. And protein folding and the conformation of those kind of biomolecules that are involved in treating really complex diseases, including cancers, that really couldn't be done by a human at any reasonable time scale. And so now that we have AI systems that can do that, that's where I see AI excelling. A lot of image recognition stuff, it's cool, it's neat, and it's going to be useful, but it's not really anything that we haven't been able to do before without, a little bit more elbow grease, so to speak. But
but it's not getting accessible to everybody. That getting accessible to lots of people. And it's interesting you're talking about the protein and so on and so forth. In a way, if you think about that, biology is a 3D printing technology.
Mm-hmm. Self-replicating machines.
Yeah. Now, when did you get involved in 3D printing technology?
Let's see, probably when was the first year I started printing? I think that was 2016 or so, as I started 3D printing. I had been interested in it, and I had been following the technology for a few years at that point. But that's when I got my first 3D printer, and it was all downhill from there. I had to keep buying printers and keep buying more and more filament. So it's been interesting.
So, I have seen you guys have a machine there that take a piece of metal and take part of it out, and then what's remaining is a device, a material, an instrument.
Yeah, we have a shop.
Yeah.
At the shop, we've got a Swiss lathe, and that is able to do what's called subtractive manufacturing. That's the keyword of the day. And then 3D printing is all about additive manufacturing.
Yeah, exactly. And I think that is what that is really different. Is about that we have the technology, what we call CNC, meaning that something like a drill, like a something comes and cuts away piece of a block, and what's remaining become what you need. So number one, what is the limitation of such a machine that, we have been doing it for probably 50, 70 years now. that have machines that they do this kind of manufacturing. What is the limitation of those CNC machines?
So the limitation is the tooling and the approaches. If you've ever heard of a two-axis CNC, that's the kind of thing that you see if you go to a craft store and you see these cut out words, live, laugh, love in plywood. That's going to be cut out with a two-axis CNC machine. And it's certainly useful for making things out of flat boards. But you start to get some more interesting designs possible when you add a third axis. So that means the two axis is where it can move in X and Y. So it can trace anything in a 2D line. Now, if you add a third axis,
Like
it means it can go...
Like a cricket machine, like a cricket, cricket?
Yes,
is a knife that goes and cuts. Okay, go ahead.
Yep. And then so you add a third axis so that it can move left, right, up, down. So that's the two axes, and it can now move in and out. And so you can now contour a surface at the same time. So a three-axis mill is very useful. And you might think, okay, well, it's all the dimensions that exist. So what's left? Well, now you got to start considering being able to machine around surfaces. So if I want to machine just a sphere, right? Doing that with a three-axis machine is possible, but I'll have to swap the direction of the part in there. So I'll have to manually take it out, fixture it back in. And in many cases, that's fine. You can get away with that. But for really complex things, you might have to change the fixturing 50, 60, 70 times in an operation if you're trying to do the kinds of cuts you need on a three-axis machine. So what do? We add a fourth axis, and that allows the tool head to move around. So it's able to move up and down, left and right, in and out, and it's also able to swoop around.
It rotates.
Yep. And four axes is great. You know what's better? 5. You know what's better than 5? 6. You know what's better than 6? 7. Those are pretty rare.
No, and then it gets even better. Then you have the machine that the tool moves, but as well the device, the block that you're cutting away, it moves as well. Then you can get to even higher the freedom, rotational and higher degree of freedom. Now,
Precisely.
Everybody can look at the YouTube. You see that what you're drilling, it's I would call it like a drill bit, something like that, can move in all different ways, but as well, while one is moving, that piece that is getting drilled as well moves and so on. It's amazing. But
yeah,
I would think you could do anything with that. What can you not do with it?
You are limited by the size and the rigidity of the tooling. So if I wanted to drill a very deep, very long, or a very long, very thin hole through something, I've got to have a drill that can do that. And that's a lot harder than you might think, because while we think of steel as being very rigid, when you have something that's 1 millimeter wide and 6 inches long, and it doesn't work so well. And so you need to consider other ways of getting that feature. And there are ways of machining features like that. It's just more time consuming and oftentimes expensive. And you end up with complications like what's called I forget the term. I think it's walkout, where the drill hole, as it goes through, starts to kind of angle off. And it's really hard to tell when that happens, because you have to stick a very small pin down there. And if it now it's jamming, well, it must have moved out. And so that's something that we're able to get around through machining, but it's costly, it's time consuming, and it doesn't always work well. And there are limits. So there are things that you cannot do. For example, if I wanted to have a hole that is drilled through something and then turns a 90-degree angle and doesn't come out somewhere, that might be something I need in a part like a heat exchanger. And if you want to look up some designs for machined versus printed heat exchangers, those are pretty cool. You can't do that. There's no way to turn a drill bit 90 degrees once it's inside a part. It's just not possible.
It comes out of somewhere that you do that 90 degree from a different angle and so on.
But again, that's where we're talking about, well, we can get around that. So you talk to a machinist, they're like, well, we can do it. We can do it. It's going to cost you, but we can do it.
Yeah. And that is about the cost. That is, I think, the most important part of 3D printing, that it lets you do, I think, very complex shapes a lot cheaper.
Yes, because the printing process doesn't care about the complexity of the geometry as long as it fits within the resolution that the printer can reach. Because
No,
you don't have tooling that has to move around. You, in many cases, well, it depends on the type of printer, but generally you don't have to have anything more than the point at which material is being added be the thing that moves around.
mhm. Now, the 3D printing technology is not as new as people think it is. So,
No, it was actually developed, I believe, some of the first 3D printing machines. Let me see if I can pull this up. Was it 60s?
yeah, but there were obviously limitation, and that limitation was the computing, actually. But let's start with the technology itself. Now,
1981 is the first.
yeah. Now, everybody has those inkjet printers, right? Do you want to describe how an inkjet printer works?
So an inkjet printer has a relatively small nozzle block, and there is a piezoelectric element in there that you apply.
Piezoelectric. Now you have to explain it. What is a piezoelectric effect? What is that?
So you apply a small amount of voltage to a piezoelectric material, and it will either move, expand, contract, flex, depending on how you've got it configured. And in these printers, they have it move, and that essentially dispenses a small amount of ink out of a small aperture, and that shoots a jet of ink, thus inkjet. And there are, in the print heads on an inkjet printer, which there can be one, there can be multiple, depends on what model you get. Some of the earliest ones probably only had one. But what they do is they will essentially scan across a section of the paper that you're printing on, and then they'll move over, do another. And so they do that band, and that band might be, let's say, 10 millimeters across, so 1 centimeter. And so it'll do it in chunks of 1 centimeter as it scans across the printer, which is why you see the printer go, yep.
Now,
And
practically, you give electric charge to the small amount of ink.
You're
charge it.
shooting a drop. You're using the electric charge directly to essentially activate a nozzle, and that nozzle shoots out a small amount of ink.
Those nozzles are tiny.
They are tiny. They're minuscule.
Yeah.
They are on the order of microns, I believe. And but
then
the way
go ahead.
the way that powder bed fusion 3D printing got started was someone saw a inkjet print head, and they're thinking, I bet if I just did that to one piece of paper and then moved it up a little bit, did it again, and then moved it up a little bit and did it again.
And
if I wasn't using paper,
instead of ink, though, that actually a piece of something, material.
Well, in this case, rather than jetting ink, they're jetting a solvent. And then instead of paper, they're using something that solvent will melt a little bit. And so that's why it's called powder bed fusion, because you have a powder, such as methyl methacrylate or acrylic powder, and say acetone is your solvent. You don't get color in this case unless you start adding dyes and solvent, and then you can start printing in color. And that was available to consumer markets a while ago. It was fairly pricey, but it's been available for a while because it's a very basic printing process that is just kind of copying the technology for inkjet printing. And
as a matter of fact, I heard that when they did the very first one, actually they did get a printer, inkjet printer, and they created a very a special kind of ink that is like a gel that would solidify, and that was the original of the 3D printing, and then layer by layer, and that process takes a long time, doesn't it?
It does, and the more print heads you have, the faster it can go. Or if you're able to use the print in each individual print head faster, that obviously speeds things up. But there is a limit, and so powder bed fusion is a very powerful technology, but there are limits, and so that's why we start looking at other printing technologies. And you might think powder bed fusion, if we can print in color and we can print in very, very small resolution, like if you look at a piece of printed, like a photo print, right, from a nice printer, you think, damn, I can't even see the pixels. That may be true, but how long did it take to print that photo? Now imagine doing that 1,000 times or 100,000 times. There's a reason why it's not the most common form of 3D printing. And then you look at things like filament 3D printing, and that can build up material very quickly because you're doing it in much thicker layers, and you're able to move a nozzle very quickly.
So somebody figured out, so this is an inkjet. Instead of ink, we drop material that they build up layer by layer to build actually an object. Now,
Mhm.
there were but some other, we talked about the powder printing, you talked about the liquid gel-like material printing, but as well, at the same time, they came up with the third kind of 3D printing technology where a laser goes into a bath of some resin, and
Mhm.
then the laser focuses the energy, and where it focuses, the material solidify there. So from these three, depositing material, melting a powder versus that resin, what is the advantage of one versus another, Liam?
Okay, so if you are melting a powder, you are limited by the scale of that powder and then the thing that you are using to dispense the solvent.
Mm-hmm.
If you are using resin, you have to have the resin cure by photochemical means. So you apply light to it. And there are two basic types of 3D printers that use resin and light. And one of those is a laser-based system, and one of them is a display-based system. So you're probably viewing this on some form of LCD screen. And if you are watching this on a projector, then hey, you have the secret third option, but we'll get to that later. A laser printer, so that would be, I believe, SLA, is something that it has a single point of curing that will scan across a 2D image, a slice of whatever model you're trying to print. And so it will cure everywhere where that laser shines and nowhere else. And then the model will move up a little bit, and then it'll cure another layer, and it'll move up a little bit, cure another layer, so on and so forth, in a pool of liquid resin. And then if you're using a display, such as an LCD screen, and this is where we start to see really cheap, and it's a good thing that these are cheap because the technology is simple. Really cheap 3D printers or resin printers nowadays, all they need is a LCD screen that can block light, and then they put a UV lamp underneath it, and you pour resin in there, and the LCD screen turns on, so the pixels turn black in areas that you do not want light to pass. And so those areas are protected from screen, and everywhere that's exposed cures all at once. So then you move up, cure an entire area, an entire slice, and that slice will be whatever image is showing on that LCD screen.
So we are talking about resin. So it's whatever you produce is some kind of polymer or plastic, right?
Right. And you're limited by the resolution of that display. So the size of the pixels is the minimum size of a feature.
What is that resolution? What do you think what that resolution is?
What is the highest pixel density display you can buy nowadays? That's what it is.
Depending on who's paying for it,
It really, exactly. Yeah. And so the technology is very flexible, which is great because if I want to pay literally $100 is enough to buy I think you could get one that's almost 1080p resolution, and it's a small build area, so it's a small screen, small build area, but that's like enough to do almost any type of small feature design that you're going to need. And then so you've got that in plastic, and now and for jewelry design, this is great. This has really been a boon to the industry because you can have someone design something either physically and they're sculpting it out of wax, and then they scan it and upload it into a program that creates a 3D file. Then you can touch up the 3D file. Then you can print either directly in a burnable wax. You can 3D print 1,000 copies of the ring you designed. And that's great. I think that's amazing. Or you can make the ring in a 3D modeling program. So if you wanted to do some kind of very mathematically perfect lattice across part of the ring, and sculpting that in wax would be just laborious as all heck. So you can avoid that and print out however many of these you want. And then you can cast them in plaster, burn out the wax, pour in the metal, and you have a functional print. And you can actually do this with non-jewelry applications as well. So if you're looking for very fine resolution metal parts, you can do, or for whatever industry you may be working in, you can get away with that. There are some considerations that have to be made, such as warping and surface finish, but just as with machining, there's ways around it.
Yeah, for a long time actually, the industry started using that to print plastic. That is the original. But when did we start thinking about that? Hey, we can as well print other material, like maybe cement or metal. I think metal was the next thing. Obviously, there's a different kind of technology was needed to make things out of metal. And now there are many different kind of for smaller object or for bigger object, there are many technologies that they let you build a structure from metal. Can you explain some of that to us?
Yeah, so I'm not sure when that was first thought of, but if the person that thought of it was anything like myself, it was probably as soon as they saw a 3D print object. They were thinking,
Yeah.
okay, we can do this with other materials, we can do this with metal. And probably
You
the
need a
first,
source of heat. That's all. That's what I'm getting at. That if you're trying to make two pieces of metal, attach them together, you need a source of heat. Now, having said that, let's talk about metals because I think that is, the most important thing that now we can print things out of metal, and
Mhm.
that's going to change truly the industry. What is
I,
a metal, first of all?
what is a
What
metal?
is a metal? Yeah. For our
Like,
audience, tell us what makes a metal metal.
well, a metal is it is a material that functions as a bunch of atomic nuclei in what is called the electron sea. So they bond in a different way than other materials fundamentally, and that's one of the things that gives metals their advantageous properties. It's what makes them workable. It's what makes them durable, and they are most often quite conductive. Um, they are generally something that can be melted in absence of oxygen and cast into various shapes. And you can alloy them to get different properties. And you can even add alloying materials that are non-metals to get to just
So
adjust the material properties very finely.
atom in a Z of
Electrons.
electron. Now I have a atom, some atoms here with the sea of electron, some atoms here with the sea of electron. If I bring them together, like two part of fluid, liquid, like two lake, I connect them together. What prevent them to go together all by themselves? What's the
Well,
problem?
uh, I can't talk quite as competently about nuclear physics as I can about chemistry and biology and 3D printing.
Actually,
But basically, there's a whole different domain of forces that come into play before you are at risk of having nuclear reactions
actually,
happening.
actually,
There's a
NASA,
large barrier of energy.
NASA figured it out the hard way.
Mhm.
When they went to a space when there's a vacuum and so on. It's
Oh,
called
you're talking about cold welding. Yeah, cold welding. So
yes, yes.
that's you're not
No,
having the yeah you're not having the nuclei bond together. That would be catastrophic to say the least.
yeah, yeah, yeah.
What's
But talk about cold welding. What's a
yeah,
cold welding?
cold welding is where you have a metallic surface free of oxygen, free of any oxide coating, and you have another metallic surface, and they connect, and now they're together. That's it. It's
How did we figure out? How did we figure it out?
so I'm sure that people had experienced this before. Well, actually, let me tell you this. People knew about cold welding for thousands of years. And you might think, well, that seems wrong. Gold leaf, right? As soon as humanity figured out how to make things out, or figured out how to get gold and found gold and collected enough of it, people were making jewelry out of it. People were making decorations out of it. And gold does not readily form oxide layers. And so you can cold weld gold to itself pretty easily. And
Yeah.
so the most visible process of cold welding is when you are applying gold leaf to something. If you overlap two areas of gold leaf and you brush them and you like kind of mush them together a little bit, they're bonded. Now it's not a perfect bond because there's some air between them, but it's not an oxide layer on the gold. It's just a barrier. It's kind of like if you had two sheets of paper that were covered in glue and you try to stick them together, there's going to be some air trapped in there, and that'll prevent those areas from sticking. But in all the areas where the glue is touching, you got two pieces of paper that are bonded together.
Not if we talked about that, the rabbit holes is taking us deeper and deeper. Now, first of all, gold can be made out of sheet that are few, just hundreds of atom across, meaning that even though gold is so expensive, gold leaves are not that expensive at all because it is so thin that you can just buy it. Some people even wrap their sushi and so on in gold, which is crazy, I think. But what's happening there, as you said, that is exactly why gold is gold. It's a very inert metal. It doesn't react with anything else because it's happy. Its electron orbits are full. Now, when that piece of metal that is clean, it has nothing on it, get into contact with another sheet of metal, preferably silver or another piece of gold or something, and then when they come close to each other, the electron from one part flows to the electron from the other part, and then they become indistinguishable. But NASA noted that when they are in the space, when there's in the vacuum, some areas that like a hatch, like a piece of metal, they got welded together. They
thought that wouldn't be a problem because they figured, oh, well, we manufacture these on Earth. We manufacture these in the presence of oxygen. So there's an oxide coating on them. So it's fine. Well, that oxide coating, especially on things like stainless steel, very, very thin. And so if just a little bit of friction and it rubs some away, and then you end up moving back into that spot, you'll end up with metal on metal contact and you get cold welding. And I forget what the gasket on that door that got welded shut was. I think it might have been glass.
Mm-hmm. But I think it's even more important, what is the best insulator to prevent electron to go from one place to another? Air. On the Earth, the air is the barrier that mostly prevent this electron to flow from one to another. In the space, there's no air, so the electron can jump from one to another, and hence, literally, you put those two pieces of metal together and they bond. Now that we knew that, now that we found out about that on Earth, we can create that actually for industrial production, create vacuum, or make it the surface so smooth and so clean that when they are together, they bond together. Now, we found out that cold bonding is as well works better if you heat up the things. And then we figured out if you heat them up to a certain degree, they bond together. It doesn't really matter. Nothing really else matters. They bond together. If you heat them up enough, they bond together now. And hence the 3D technology of the powder. Talk about the powder, because yesterday you were telling us that powder literally burns. I mean, it's a metal. How does a metal powder, or how does a metal burn?
So remember when I talked about metal oxides earlier?
Mm-hmm.
Metal oxides are very important to industry. If you think about stainless steel, what makes stainless steel stainless, right? Why are surgical instruments made from stainless steel? Because they form a chromium vanadium rich oxide layer on the surface.
On the outside, so it has certain percentage of other metal. The iron itself does oxidate, but when it oxidates, it breaks. It sort of has fracture. Air goes deeper and deeper. But there are some other metal. As a matter of fact, there are lots of metal that oxidate so fast, so smooth, they create their own barrier against the oxygen. Please go ahead.
Aluminum is an excellent example of that. Titanium as well. So titanium will form a protective oxide layer.
But that's why they don't rust. That's why we love them.
That's why we love them. But now if we're talking about printing something out of titanium, for example, I wouldn't know anything about why we would be doing that. But if we have a titanium powder and we want to print something from it, or we want to just, let's say we're bonding a bunch of titanium powder together, whether we're printing something or not. The main challenge there is we need to make sure that there are not oxide layers around those particles protecting them. And doing that is very challenging in most environments. So what you oftentimes need to do to have the best performance is, and to be clear, the type of printing we're talking about does not require vacuum, and it does not require there to be zero oxide layer. That just makes things turn out better. So you want to create the powder that you're going to use for printing in a low oxygen or no oxygen environment so that it is almost.
How do you do that?
I believe that they they cast a billet of, actually, no, that's probably not how they do it. I would imagine that it is chemically precipitated from a solution, and in order to get the very tiny particles that you need of titanium,
the particle size, like even gold, when you mine gold and so on, most of that, to get the gold out of the thing is literally a chemical process. And then once you get the gold, it's like a powder, and then you melt it, it becomes gold bars and so on. That's how you get the gold out of, I mean, those days that you go and find a gold nugget and so on, those days are over. The industrial production of gold is literally putting a very aggressive acid that even dissolves the gold, and then separating it, and then giving it that solution, other metal, that the acid like that other metal much better, and literally with small atom size, it's of the particle of gold participate. So all the powder that you use for 3D printing, I'm assuming, is produced chemically the same way. What do you think?
I believe that is probably the case. It could also be produced.
You cannot grind it. You cannot really grind it to that.
You can grind powder, but I would imagine that would be a very labor intensive process that we can probably automate. In fact, you know what? Why speculate? We have connection to the internet.
Okay, you have this powder, and then you have to have it in the oxygen poor or oxygen free environment before you can, like layer by layer, go with the laser and heat it up so the particle get attached together, correct?
Yeah. So what you're doing is you're creating a very small melt pool, and this is not the same as cold welding, because cold welding is kind of, it's a good indicator of where there is and is not an oxide layer present. And so if I wanted to cold weld titanium to titanium, one way of doing that is, and this sounds kind of silly, but you can take two very smooth, clean titanium surfaces, and then you can put them in a oxygen-free environment, such as under argon gas, and then you can clean off the oxide layer either with a chemical etchant or mechanically by using a blade to scrape off that top layer, and then you can slide them together or just press them together and wring out the trapped air, the trapped argon gas, which is non-reactive, and you will have a decent cold weld there. But with 3D printing in powder materials, the getting rid of the oxygen is more about the final composition of the part that you're worried about, because you want to have a low oxygen content in the final alloy. Because as we talked about, protective oxide layers are great on the outside of things, but they are brittle. They are not as strong or not as ductile as a solid metal. So you want to reduce the amount of that is present inside the part that you're printing. So you print under an inert atmosphere, and you print.
What is an inert atmosphere?
Argon. So argon is a really good one.
Okay. What is argon?
Argon is a noble gas. Much like gold, it has full electron shells and it does not react readily.
Is it like helium?
It is like helium, yes, but it is a lot heavier.
It is in the same, kind of periodic table column like helium, but because it's heavier, it doesn't evaporate away from the Earth.
Correct. In fact, I believe our atmosphere is something like 0.2 or 2% argon?
I think it's less than 1%, but why don't we look it up? Because I think argon is something that we use it in lots of technologies, right?
0.93% oxygen or argon.
Under a percent, just under a percent. But that's a lot. That means that we have a lot of it.
Yeah, and fun fact about argon, and if anyone watching this is interested in seeing someone breathe argon and hear their voice when they've breathed argon, check out the Cody's Lab video on breathing argon or breathing all the noble gases. He
what
even breathes
happens
some radon. I don't recommend doing that.
Why would anybody do that? Huh?
It was a small amount. It was fine.
Okay,
but it makes your voice lower because the speed of sound in argon is different than it is in air.
yeah, so everybody knows if you have a helium, you talk and then your voice pitch become higher.
Yep.
But obviously, if it's a heavier, molecule, then your voice become deeper. Yeah, makes sense. Now, okay, so we have the powder of certain particle size in a chamber with low oxygen. We practically get rid of the oxygen by flooding it with argon.
Mm-hmm.
And then the laser, and argon is a noble gas. That means the outer electron shell are full. It doesn't like to react with anything. Okay.
Correct.
So, and then your laser comes layer by layer, adds more material. And then every time it's done with one layer, you lay on another layer of this powder, whatever it is. What is the resolution of a product like that?
It does depend on the printer. And so the maximum resolution would be whatever the size of the particles is. And that is something that is technically possible, but is incredibly difficult to practically achieve. And so oftentimes the resolution is set to be roughly the same as the spot size of the laser. So the size of the laser melt pool will be the resolution. So if you do a layer that is as thick as the melt pool, and that can be thousands of particles thick, then, or depending on the size of the particle, then that's going to be your thickness of layer, and thus your Z height resolution.
Yeah, well, I can imagine that if it's really that thin, you're layer by layer so thin, I can imagine it can take days and days to print anything.
Yeah, so depending on the size of the object being printed, it can take anywhere between a couple hours or even a couple minutes to days, weeks.
Really?
Yeah, again, there are companies that are printing things like engine blocks out of aluminum, stainless steel, all sorts of
You can print aluminum.
aerospace parts. Yeah, you can print with aluminum, but again, has to be processed and kept more oxygen free to get good results. And to be clear, when you buy the material that is like ready for 3D printing, generally it's in a sealed container that is already oxygen free, because as soon as you open it, it's exposed to oxygen, and now you're going to have oxide layers around all those particles, which is going to reduce the mechanical performance of your print. And then you put it in the machine, and the machine flushes it with argon, and so you're good to start printing. But anyway, so the spot size of the laser means that that is the area that is going to be printed, that is going to be solidified at any given time. And so if we want to speed that process up, we can make the spot size bigger. And we can also...
The resolution becomes
yes,
much bigger.
Right, exactly. And so very advanced laser systems can have multiple small spot sizes going at once. So you can have up to, well, there's no practical limit. It's just how much money do you want to spend on lasers? But you could have, there are systems available with 4 lasers, 10 lasers. I'm sure that if you wanted to, you could create a 1,000 laser system that could print stuff faster than anything else, but that would be horrifically expensive. So most systems are 1 laser, maybe 2 lasers if you're feeling frisky. But the spot size is the thing here, where you can have a very small spot size and you can have a very large spot size. You mix those and you say, I'm going to get very fine resolution in this area with a small spot size laser. And then I say, I'm going to fill in this solid area with the large spot size laser. Then you can do things significantly faster. But that's just a tuning of the parameters of the actual machine. The technology is still functioning exactly the same.
Yeah. Now, I remember years ago, I bought a 3D plastic printing machine, a printer, and if you would look at it, you would immediately know, okay, this is layer by layer. You would see the individual layers and so on. How good is technology getting these days?
With plastic printing specifically?
Both plastic, metal, whatever. I mean, if you get that device in your hand, can you just say, definitely, this is a 3D printed thing?
So if I'm printing something from metal, whether it's stainless steel, titanium, aluminum, whatever, oftentimes the surface finish is very uniform and to the point that you can't see the layers, but you'll see a slight roughness. And if you look at my background here, you can actually see some examples of parts that, see if I can pin myself. Yeah. So this right here is the kind of surface finish. You see, it looks kind of like grainy, kind of pebbled. That's what you'll see. And so this is the metal powder being dumped in.
And I see things that on top is the laser on the second, on the top.
So I actually have a range. I have a range of 3D printing technologies being shown here. I can go through these in a minute, but to talk about the resolution and the layer lines for metal 3D printing, I don't know if you can see layer lines on that. I can't really. It's not helped by the fact that the image resolution isn't super high. But if we look at this, we can kind of see some striations across it, and that's because this is a different process. If you see, this is a nozzle that is dispensing material that is then being welded on. I think this is using either plasma or a laser is coming in at the same time.
Almost like a TIG welder that moves around and deposit molten. Yeah, I have seen that they make actually part of the space shuttle and part of the rockets that that's very complex. That they're building it like a TIG welder. Imagine that goes like in a 2D.
Yeah, I believe the company that's doing that is Rocket Lab, and they're using what is essentially a modified welding
on a robot, on industrial robot.
And their most impressive innovation is the thermal compensation. So as you print something and heat gets dumped into the area that you're printing, that because you're printing with metal, there's a lot of warping that happens, several percent at times. And if you just pretend that it's going to be a perfect circle every time, you're going to end up with a very warped final product. But if you predict and you use math to determine how it's going to work as the hot spot moves around and as it dissipates, you can move the print head just a little bit to compensate for that, so that once it cools, it unwarps and you are back to a perfect cylinder in the case of the rocket hulls. But anyway, so the layer lines. In a powder bed fusion style of metal 3D printer, oftentimes you cannot see the layer lines. You can see a surface finish. There's a certain roughness to it, but that can also be removed via post-processing by either a chemical etch, or if it's steel, you can do electrochemical, which is really great. And then you can also do something like media blasting. So you can hit it with glass beads, and very, very tiny glass beads, and that smooths that surface. You can even do what's called burnishing, where essentially you rub the surface.
Post-processing, is it what it's called?
Can you repeat that?
Is that what you're describing? Is so-called the post-processing, that you build it, now you want to change the surface and so on?
Yeah, if you want to change the surface, you can very easily post-process most metal printed parts, and they will appear to not be printed. Other than that, their geometry is quite complex in many cases.
I can wrap my head around it. No matter what, layer by layer, you're depositing material. We talked about the plastic, we talked about the metal, various kinds. What other material can you deposit and build something? What is the technology? Where is technology heading?
So, as a biomedical engineer, I can predict that many people in my position would talk about tissue 3D printing. I think tissue 3D printing is an utter waste of time. Because, as you said earlier, biology is basically just a bunch of very complex 3D printers in a way. You're growing things. So we could talk about biomedical 3D printing using tissues. It'll get done.
Very rudimentary. I have looked it up. It is very rudimentary, but there are two techniques there. One technique is actually they spray cells, and then the other techniques, they spray some collagen matrix and then impregnate it with stem cells. Then it seems that if you have a certain shape, structure, skeleton, like from collagen, cells can find their way and so on, but it is very rudimentary. So tissue printing.
Yeah, it will advance, and we'll be able to do more interesting things with it in time, but I do not predict that it will outstrip the progress that we're going to see with genetic engineering of things like immunosuppressed pigs. And so if we have a pig that is immunosuppressed,
it
and
it's more than immunosuppressed. They do go, and with the method, they go and cut out certain protein in the pig and insert another. Literally, they put a DNA in that pig that it makes human protein, not a pig protein. So all of a sudden, you can just have a pig that the parts can be used in human because they are biocompatible to human. So I think
they are cellular. They are identical. In many cases, they are cellularly identical, and at the very least, they are identical in the extracellular tissues. In many cases, and in the near future, we will be able to, and this is partly due to being able to have AI do better protein folding and protein generation, and decoding the DNA sequences to produce proteins that we want. We'll be able to have the future is good. Future is good. And some people are really unsettled by the idea of like, oh, it's like a half human, half pig. It's like, no, it's a pig. It's still a pig.
It's a pig.
It's a pig. The pig will have no difference in experience. It's not having human thoughts. There's no human brain proteins happening there. Now, human brain proteins are special, and if we want to, we can.
I'm happy Amanda is not here because Amanda would disagree with you.
Hey, pigs are actually shockingly smart animals.
They are very smart animals.
It is kind of unsettling that we eat them at all. Like not to neither here nor there. I don't eat pork, but if I did, I would feel bad about it. Okay.
Now you open a can of worms. You don't eat pig?
No, I'm allergic to it.
Oh, okay. Well, that's a different episode. We will talk
completely.
About that. Yeah. Okay. So, but okay. Printing tissue. That is a technology that you're just starting to experiment with. So what else?
It's been in process for a while. It's slow. It's something that has very limited use case because you can print a blood vessel, but it's much better to just harvest a blood vessel, decellularize it, and then recellularize it with human cells because you get better results.
You're doing it already.
Yeah.
And so taking a heart, we wash it, everything away, and populate it with human cells and so on. You're already doing it. That's actually, I think, like you. I believe, like you, it's more promising than the printing 3D. Yeah. But have you watched the movie Fifth Element?
I have, a long time ago.
When they take this leftover piece of that alien, and then the machine recognizes it, and then goes layer by layer, and then
that was a very funny animation that they did for that, because that is not even the amount that would work is zero.
But so what else can we print in a 3D, like layer by layer?
We can print in biomaterials, which is, in my opinion, much more interesting. If we're printing in things that match extracellular matrix of various tissues like bone or collagen or cartilage, and you can do adipose tissue, and you may think, why do we want to print fat? Well, there's a lot of good reasons to.
Okay, biological tissue.
Biological tissues, yes. Either acellular or you just have cells mixed in there, and it's no big deal. That will have a lot of use. And being able to print things in biocompatible tissue or biocompatible materials is even more important because it's not nearly as sensitive to the printing process. Like if I take chipped up bone material and I 3D print something out of that chipped up bone material, I don't have to worry about killing cells because there's no cells in it. Or if there were, I don't care if they're dead because I'm making a part and it's supposed to be made of hydroxyapatite, right? That's the point of it. And then I can now take that hydroxyapatite material and I can put it in the body in a place where it is going to, over time, be replaced by living bone.
And lots of people are now talking about the 3D printed body parts. Like certainly you can do it with a piece of bone, replace it with other material, plastic or metal and so on. But now that you're talking about 3D printing tissue part, have you heard of that company that 3D prints cakes, birthday cakes? Have you heard of that?
I have not. Let me take a look at that.
Yeah. Now, And
The
obviously,
3D print with chocolate, I've seen that.
yeah, yeah. Now, I'm not sure. I used to be a big Star Trek fan,
Mhm.
and I was always, so in shock and awe of that replicator that you just tell it what to do, and it makes you that food. And it seems that there is actually some companies that they take different material and literally they print you a food with certain texture, with a mix of material, basic material. I think that's at this point, I think is more like a gimmick than a real thing.
For certain, yeah. Being able to precisely mechanically produce food is the more interesting thing than 3D printing, because if I can 3D print cake, right? So it perfectly bakes as it comes out the nozzle. That's cool. It's probably not going to have as nice of a texture as a piece of cake that was extruded as an entire chunk or otherwise baked in a pan. But if I can then pipe the frosting on automatically and create really complex designs, hey, that's pretty cool. What I'm seeing here is it looks like people are 3D printing molds and then making cakes out of the molds, which that is the more interesting and useful thing, because you can reuse the mold many times and you don't have to have $1 million+ machine printing a food safe to eat cake. But being able to replicate food in very precise, being able to chemically recreate food from building blocks is going to be a very important thing in the far-flung future. But we're not really very close to that yet. But I do look forward to seeing that when it eventually comes about.
Now, there is an episode of the newest something similar, science fiction, that they travel back in time, and this guy is horrified that he has to kill animals and eat them, because in the future, obviously, they don't do that. All their food is replicated from a machine, and he's so horrified.
So one thing that I think a lot of science fiction does when they talk about like future foods is they tend to assume that a lot of things that are, they're ethically not great. They're not good, right? Killing animals for meat, no matter how sentient or not sentient they are, it's probably best if we could avoid doing that in general.
That's the closest you are to Amanda, I eat anything, If it moves, if it doesn't move, and so on, I eat anything.
Well, I will say that I would be happier. I do eat beef. I would be happier if I could eat beef that didn't involve a cow being killed.
Yeah.
But
there is that. You can do that. This lab-grown beef is like $5,000 per hamburger.
Precisely. And so the problem is, and the problem will always be, producing something that looks, tastes, and has a nutritional content of meat, or I should say looks, tastes, and feels like, and has the nutritional consistency of meat, is always going to be more expensive than, say, for example, using genetic engineering to create a thing that create like a sessile animal that has no brain and just produces a big muscle mass.
No, just muscle. No, that is one of the things that, by the way, I cannot avoid to tell you a joke.
Oh, yeah?
The joke is that if the cow doesn't want to be eaten, why is it made of food? So now, but that's one of the things is that when we eat something, we just relying what nature put in it. But if we truly compile it with our knowledge of what our body needs, we can make a steak that is just for your metabolism the best, or versus somebody else's metabolism. We can truly individually manufacture that, like especially if you're going to send the people to Mars or somewhere else and so on. That is become more important, that we create something that is individually adjusted to that person. So that is one consideration. We are getting close to the end of our session, but we haven't finished that without talking about concrete printing.
Oh, yes. So, we can. So, the main difference between concrete printing and other similar materials is that those materials cure as they are exposed to oxygen and as well, no, that's not true. Some materials that print in the same way that concrete does are cured by oxygen. Other materials are cured by carbon dioxide. Yeah, it's a chemical cure. So the concrete, it's mixed, and then as it's being extruded, the reaction that is causing it to cure and harden is already happening. It's just not done yet, so it stays a paste for longer. So concrete printer is a paste style printer, and other materials like hydroxyapatite or calcium carbonate could be used, and like even plaster would work. And so you're able to extrude either let's just call it a wet material, and then as it dries, whether that's chemical curing or actually drying, you're able to create a line material. And oftentimes this requires a larger nozzle, just because these types of materials are prone to clog smaller nozzles that you'd see in a printer like this, where that's about a 0.4 millimeter nozzle. The process is largely the same as a traditional FDM or filament deposition model 3D printer. So this type of printer, it works the same as a concrete printer that's the size of the building.
It's just bigger amount of material that's getting deposited.
Correct, yeah. So it's a larger amount of material. The mechanism to move the concrete from the mixer to the nozzle has to exist, and it's going to be different than just a gear that turns and moves the filament down. So there's more things that can go wrong. The concrete printing technology is unfortunately not a mature technology, because the companies that produce the machines that can do concrete printing, to say this nicely, I don't think most of them were familiar with 3D printing, and they tried to do too many things by themselves. When I look at the types of machines being used, they're closer to a CNC machine that uses like machine G code, and it's just not, it's not great. Whereas if you,
it's not matured, I would say. Yes,
it's not matured, but the solution is very simple, and that is you take the software that has untold numbers of human hours of effort put into it, because it's been open sourced for desktop style 3D printers, where people have made custom features, suggested things, improved things hundreds and thousands of times to make this software really amazing. Because like desktop 3D printers, it's just a nozzle and a heater and some motors that move it in X, Y, and Z. Like, it's a simple machine. The software being able to use the voltage feedback on the motors to detect, oh, am I like touching the print bed? So I can level the print bed automatically. And then I can also detect, based on like a simple sensor that we add on, that whether the print is proceeding well, whether the nozzle pressure is getting too high, indicating there's a clog, and then it automatically alerts someone, or it pauses the print, clears the nozzle, keeps going. Like, there are many things the software can do that just companies that are currently doing or trying to do concrete 3D printing, they don't have that, because they decided, we're going to do it ourselves. We're going to control the software. We're going to keep it closed source. We're not going to use readily available desktop 3D printing software, just scale it up. Yeah. And there are complications to using that, but none of them are insurmountable. So the companies that are the most interesting, in my opinion, that are doing concrete printing they're doing it more like this machine, where it's able to move in 5 axes. So rather than 1, 2, 3, it's able to move in
multiple axes, like an industrial robot that has more than 3 degrees of freedom.
Correct.
Now, we are getting close to the end, but where do you think we are heading? And number one, and number two, if you could influence this field, what do you want to see in this technology in the future?
In 3D printing or concrete 3D printing specifically?
No, in 3D printing generally. Where are we heading? What's your opinion? Where are we heading? And where do you think, what's your wish list?
I think that people that are most interested with 3D printing, and industries that are using 3D printing, need to treat it more like another run-of-the-mill manufacturing process. Because in a lot of cases, you see companies that they say, oh, I'm going to, or not companies necessarily, but people who start a company based on the idea of, oh, I can 3D print, let's say, a house, or I can 3D print an implant. And then they try and get the 3D printer to do every single bit of work that needs to be done to make the final item. And that's just not good, because like, try to think of a product that is made by doing one thing. even the like Stone Age technology. You take a piece of wood and you nap away, the excess material. You've done a subtractive manufacturing process, and now let's make it a spear. Okay, let's start napping a spear shaft out of stone. No, you're not going to do that. You're going to take the thing. You're going to split a piece of wood, and you're going to tie it on there with a gut twine or something. Like, you're using multiple materials, you're using multiple processes, and you're using the manufacturing method. And so we're talking about 3D printing in a kind of roundabout way. You need to use that as the best way to do one thing. And so for implant 3D printing, we need to be doing printing of complex geometries, and then finishing or processing to get any other extra features that we want on there that are otherwise laborious or maybe even impossible to 3D print. And then for like tissue printing, if we need to 3D print the shape of something, we need to be able to have we print the scaffold, and then we seed it with tissue, and then we put it in a model that is able to simulate body conditions such as blood flow. So if we print a basic blood vessel, we seed it with endothelial cells, and then we start flowing blood through that, and you increase the amount of pressure that has to hold over time in a very dynamic system, you're going to be able to create an almost perfect blood vessel. Mm-hmm. And that concept of using 3D printing as kind of not as little as possible, but make it as little of a deal as possible. Because it's like, oh, we're just 3D printing the scaffold. The rest it's all about the cells. It's all about supporting them, giving them a biologically similar environment. And for house 3D printing or large structure 3D printing in general, we need to treat that as just a building block in the process, where we can use this in a way that it is most efficient. Because if we can print, the entire outer contour of a house on site, that's great. But how many things are you actually, or how many of the building processes are you actually saving? You still got to run conduit, you still got to run the electrical lines, you still got to run water, heat, air, blah, blah, blah. You still got to add insulation. You got to do all these things. And then especially if you're, pouring concrete into something, that's another process. So you want to use the printing to create as much value as possible with as little effort as possible. And in many cases,
economy of it is going to dictate where we are going.
Yeah. And I've seen like the worst offenders are companies that say, oh, we're going to 3D print an entire house. And then they print the entire thing and do almost nothing to it. So it looks like this kind of wasp nest that is like, okay, I guess it works. It's not pretty, and it probably isn't warm or energy efficient. So why are we, and they charge out the nose for it. So you need to make it as cheap as possible. So if you're going to use 3D printing to make it cheap. That's what's compelling. If you're going to use 3D printing to make it easy to put together, use pre-assembled insulation panels so that it's energy efficient, or have lots of thermal mass in the walls because you print them hollow, and then you
and that is concrete. The point. Yeah, that is the point that I want to close with, is that what you just said, you print it, but then it's not functional. I think the future is, and I think it's an achievable future, is print the function into the structure.
Yep.
And
don't be afraid to add on to it with other technologies. Absolutely. Printing is great, but we have this whole industry of other technologies that are in many, many ways better than 3D printing I don't need to go into it, but there are many technologies that are just as impressive as 3D printing.
Yeah.
They're older. They're not as new. They're not as flashy.
What I see us being in 10 to 20 years is that the printer prints multiple different material, combines them in proportion that after some processing, the material have different characteristic that the function is printed into the whatever you're doing, like a wrench that it does something, a house that has electrical wires in it, a device that it changes the shape because it's printed as such that it changes the shape to achieve a function that is very unique to that thing, and so on, and that at different various scales. I'm talking about from macroscopic to
I'll tell you right now, those are going to be two different machines at two different scales, many different machines at many different scales. But there is a coming time where we will be able to print something like a cell phone. That doesn't show up at all. You can print something like an entire cell phone, laying down layer by layer with a machine that I don't want to talk about the exact function too much, because I actually do have a a design for this that I've never seen anywhere else. But point is, we'll be able to lay down individual materials, not quite atom by atom, because that would take too long, quite frankly, but in thicknesses that rival like nanometer thick layers and nanometer size spots.
Oh, you're already doing it. That's how the chips are produced, the computer
Right,
chips.
that's how the chips are produced. But the chips ultimately are several layers, and they take billion-dollar machines.
Yeah.
And in theory, we can have the level of printing that I'm talking about with maybe a $200,000, $400,000 machine.
Too much.
I know. It's. I will just say, think about if you're trying to think about ways to improve 3D printing technology. Think about how 3D printing technology has been developed in the first place. It's always based off of some kind of display technology.
Yeah.
Always some kind of display technology.
Well, it was really very, very interesting. We are coming to close now, and stay tuned. Lots of good things are going to happen. And at the end of the day, I think it's going to individually change our lives, because many things that would be extremely expensive is going to get cheaper with this technology.
Oh, yeah.
Many things that wouldn't be possible is going to be possible, but it's always a technology that I think is worth to follow in your personal life. So thank you very much for everybody. For Essence, I'm Dr. Abbasi, and I'm my special guest.
Hi, I'm Liam Groom. Thank you for tuning in.
Okay, thank you. Bye-bye.